Welcome to this quick session about momentum questions. The questions from this have been taken from the Pearson Edexcel A-Level Physics 2 by Miles Hudson. This is our standard textbook. I have included the questions on the video because the Year 12 students that I have do not have this book yet. This is Year 13 content. They've finished all the Year 12 content, so we're just remotely putting them through the Year 13 content. Okay, so question number 1. What is the impulse needed to stop a car that has a momentum of 22,000 kilograms meters per second? And then, if the car brakes could apply a force of 6,800 newtons, how long would it take to bring the car to a stop? So to answer this question, we have to know what impulse is. Impulse is measured by force multiplied by time. But it's not just that, it's the change in momentum. So if the car already has momentum and we're bringing it to a stop, we're taking it from its initial momentum to 0. So that's its change in momentum. So the impulse is just the change in momentum. So as we're going from 22,000 kilograms meters per second to 0, then the change in momentum and therefore the impulse is 22,000. So that's 22,000 newtons seconds. So the second part, impulse is force multiplied by time. Therefore, we can rearrange this to give us time is equal to impulse divided by force. 22,000 kilograms meters per second divided by 6,800 newtons is going to give us a time of approximately 3.24 seconds. All right, so this one is much more interesting. We're going to look at practical application of two-dimensional momentum now. Imagine that you're playing pool. If you can imagine, after the lockdown, we are now in a nice bar where we can play pool or a pool call, and we're taking a shot on the black. We're lined up perfectly. The black is sat right in the center of the end of the table. The white ball is positioned exactly between the two middle pockets. Now, both balls have exactly the same mass. They are both 0.17 kilograms. Now, if you recall the last video, then I spoke to you about what happens if two balls of the same mass will collide together in an ideal world. So the white ball's been struck and it's traveling at 6 meters per second. The black ball, which is stationary, then travels away at 45 degrees with a velocity of 4.24 meters per second, and that sinks into the corner pocket. Hooray, we have sunk the black and probably won the game. But what I want to know is what is going to happen to the white ball. Now, there are some instinctive answers to this, but the best thing to help your practice, what I want you to do is resolve the components of the black ball's momentum and then find out what happened to the white ball. And then after that, is that an elastic or an inelastic collision? So here's our scenario. We have our pool table, we have our cue ball sat ready to go. The mass of the cue ball is 0.17 kilograms and its velocity when struck is 6 meters per second. The mass of the black ball, again 0.17 kilograms, and it's sat stationary, completely unaware of what's about to happen. We know after it has been struck, the black ball now still has a mass of 0.17 kilograms. Its velocity is now 4.24 meters per second at an angle of 45 degrees. So what's going to happen to the white ball? Its mass isn't going to change, but what is its velocity and what angle is it moving off at? And how are we going to work this out? The first thing to do when we're going to break down the components of the momentum of the black ball. So let's start with the horizontal component. We know that momentum is 4.24, that's its velocity, multiplied by its mass, 0.17, multiplied by the sine of 45, because that's the angle it's moved off at. And this gives a momentum of 0.51 kilograms meters per second. So now we move into the vertical component, and we find the calculation is exactly the same. 45 degrees is that magical angle where both sine and cos are the same. So that gives us a vertical component of 0.51 kilograms meters per second. So what about the white ball? Well, let's have a look at the total momentum in the horizontal direction. The momentum before has to be the same as the momentum afterwards. So if we have the momentum of the white ball plus the momentum of the black ball, should give us the momentum of the white ball plus the momentum of the black ball after the collision. So that's W prime, B prime. We can rearrange this equation to give us momentum of W prime is equal to momentum of the white ball plus the momentum of the black ball minus the momentum of the black ball after collision. So if we work that out, the momentum of the white ball after collision is equal to the momentum of the white ball in the horizontal direction, which is 1.02 kilograms meters per second. That's 6 meters per second multiplied by 0.17 kilograms. If you add that to 0, because the black ball isn't moving, and then you take away the momentum of the black ball after the collision. So you find that 1.02 plus 0 minus 0.51 gives 0.51 kilograms meters per second. That's perhaps not very surprising, as it's exactly the same as the white ball, as the black ball, and that's what we expect. We expect really the momentum of both balls to be exactly the same, or very similar. So if we resolve the momentum in the vertical direction now, we do exactly the same thing. The momentum before is the same as the momentum after. So now we rearrange the equation exactly the same way. The momentum of the white ball after the collision is equal to the momentum of the white ball plus the black ball before the collision minus the momentum of the black ball after collision. Now in the vertical direction, the white ball has no momentum. It's not moving in the vertical direction, and neither is the black ball. However, after the collision, the black ball is traveling in the vertical direction, has a momentum of 0.51. So therefore, the momentum of the white ball after the collision is now negative 0.51 kilograms meters per second. Remember, it's a vector, so it has a direction. Okay, so have we got conservation of kinetic energy? Let's have a look. So if we have conservation of momentum, we always have conservation of momentum. That's a fundamental law of the universe. We can't change that. However, in this, if we've looked at the velocity of the black ball, we've now calculated the velocity of the momentum of the white ball. Have a look at the kinetic energy. Is the total kinetic energy before the collision the same as the total kinetic energy after the collision? In our previous video, I described to you how you could derive a Pythagorean equation from this. If you haven't seen that, I'm going to stick a link above. A little info card is about to pop up right now to that video, so you can have a look. Okay, so doing this Pythagorean equation, I've got 1.04 for the momentum of the white ball before the collision squared. Is equal to 0.52 plus 0.52. That's the momentum of both balls after the collision squared. And you can see 1.04 does indeed equal 0.52 times 2. Okay, so therefore kinetic energy is conserved, so we have an elastic collision. What does that look like then? So we have our ball. We now know that the velocity is 4.24 meters per second, and the angle is 45 degrees. So we strike the cue ball, off it goes, it hits the black ball, and despite having won the game because we've potted the black, we've also potted the white, and we've lost the game. Our celebrations turn to tears, and we're all doomed. So why doesn't this happen in pool? If you made that shot in pool, on a normal pool table with two balls exactly the same mass, why would that not actually happen? You would not pot the black if you hit the ball straight on, and the white would also not pot. Why doesn't that happen? We've just mathematically proved that it does. The answer to this, obviously, is that kinetic energy is not conserved in the reality of this case. It's not an elastic collision. This calculated example is an elastic collision, but it could only be an elastic collision if you were on a completely frictionless surface and the balls did not make a sound when they struck. Part of the appeal of pool, obviously, is the sound of the balls smacking into each other. and that takes out that energy, so it reduces the energy. So you do not have a 90-degree separation between the two balls. So don't go play that shot thinking that's going to sink, because it isn't. You're going to miss. It's going to hit the just below the corner and get some weird bounces, probably laying your opponent for an easy shot. Okay, so let's have a quick look at question 3 and question 4. Question 3, calculate how fast the impactor spacecraft in figure E would have to be travelling if it is to alter the Apophis asteroid's trajectory by 1 degree. Comment on the answer. Well, obviously that makes absolutely no sense because you can't see that figure E, so here it is. So first, a little bit of background. This is directly from the textbook. So, on the 4th of July in 2005, NASA sent out a deep impact mission, and that actually succeeded. It crashed a spacecraft into a comet called Tempel 1. There you go, figure D, big giant comet there. That mission, the impactor spacecraft had a mass of 370 kilograms, but the comet was 7.2 times 10 to the 13 kilograms, a massive difference. So there's absolutely insignificant change in the comet's trajectory. So this was really to study the comet's composition, but there is an asteroid named Apophis, which is on its way towards us, and we think, by calculation, in 2035, 2036, or maybe 2037, this is going to be a near-Earth object. This is a bit of a worry, because how near to Earth's orbit is it actually going to get? There are some predictions that say it's actually going to hit us with the force larger than 3 times the amount of the explosives used in World War II. That's a lot. We don't want that. That's kind of extinction level event. So they're looking at whether an impactor mission could succeed. Now, if this sounds familiar, it's probably because it's the plot of at least 3 different science fiction films from the early 2000s, some of which have terrible, terrible acting and are terrible, terrible films. One of them's okay. So the question is, can we send an impacting craft to knock this asteroid out of the way? Now, the asteroid is 6.1 times 10 to the 10 kilograms. It's traveling at approximately 12.6 kilometers per second. They think that you will need a 4,000 kilogram impactor craft traveling at 6 kilometers per second could actually alter the path enough to stop us all from dying. So let's have a look at the maths of that. So here we go. Here's what that would look like. Now, this is similar to the rocket and the asteroid impact that I showed you in the previous video. So you have your asteroid traveling in the horizontal direction at 12.6 kilometers per second. The impactor craft is traveling in the vertical direction, so there are no crossover components. One is traveling the vertical component, one is traveling in the horizontal path. Okay, so you can calculate the momentum in both directions, and it's just the momentum of each object. So the momentum of the asteroid, which is traveling in the horizontal plane, is its mass times its velocity. So 6.1 times 10 to the 10 multiplied by 12.6 times 10 to the 3, and that gives you a whopping momentum of 7.69 times 10 to the 14 kilograms meters per second. That is huge. How is this little tiny impactor craft going to compete with that? Let's have a look at its momentum. Again, mass times velocity, it's 4,000 kilograms. 4 times 10 to the 3 multiplied by 6 times 10 to the 3 meters per second. That gives you a momentum of 2.4 times 10 to the 7 kilograms meters per second. If you resolve that into a triangle and look at the total momentum after the impact, again, I refer you to my previous video on how to work this out. So you can work this out with Pythagoras again. You can work out the total momentum of the asteroid and impactor craft combined. And if you look at that maths there, you'll see that the momentum afterwards is 7.69 times 10 to the 14 kilograms meters per second. That's exactly the same as what it was before. We have made absolutely no difference to its momentum. And if you look at the velocity, it's still 12.6 kilometers per second. We have made zero impact in terms of its momentum and its velocity. And that's not too surprising. We've pretty much thrown a teeny tiny foil cup at a massive boulder. So why is this significant? Well, you can look at the angle of the new impact, the new momentum. So again, if you look at that triangle, you now have a momentum in the horizontal direction, a momentum in the vertical direction, and so you have an angle between them. To do that, you do tan to the -1 of the magnitudes of those momentums, and you find you have a change in the angle of 1.79 times 10 to the -6 degrees. That's 1.79 microdegrees. Again, super, super tiny. And if we did this close to Earth, we'd all be toast. It would hit us all and we'd all be like the dinosaurs, completely extinct. However, if you do this far enough away, then it's going to change the position roughly about 30 kilometers away, and that's enough to change it from a deadly impact to a near-Earth object. So this is what we're trying to do. Obviously, if you make it slightly bigger, it's going to have a slightly better effect. And so the question says, how can we alter the asteroid's trajectory by an entire degree? Let's be sure. Why do a couple of microdegrees when 1 degree would be a massive difference? So let's have a look at what we'd need to do that. Okay, so as I've just said, the angle is the inverse tan of the momentum of the impactor divided by the momentum of the asteroid. So the tan of the angle is momentum of the impactor divided by momentum of the asteroid. Rearrange this to get the momentum of the impactor that you'd need. You have the momentum of the asteroid multiplied by tan theta. So plug in those numbers. The momentum of the impactor is 7.69 times 10 to the 14 multiplied by tan of 1. And that gives you a total momentum of 1.34 times 10 to the 13 kilograms meters per second. That's the momentum of the impactor that you would need to cause a change in direction of 1 degree. So what's the velocity of that? Well, now we divide that by the mass of the impactor, which is still 4,000 kilograms, and we end up with 3.4 times 10 to the 9 meters per second. Apologies, that's a mistake there. So that should be meters per second. And what's wrong with this? Why can't we project an impactor vehicle of this speed? Well, quite simply, that is faster than the speed of light and therefore completely impossible. That would create an infinite mass as it approaches the speed of light, and therefore create a bigger problem as it creates an infinite black hole that sucks us all into oblivion. So this isn't possible. We cannot physically accelerate a small craft of that size into the asteroid to make a 1 degree change. We could make it bigger, we could make the mass bigger, but obviously then we're increasing lots of other factors. Okay, now before we move into question 4, this is just a brief overview of the experiment that you do have to do in the lab. It's one of the required practicals for Edexcel. It's a CPAC. So we have a camera focused on a table or a surface. We have a ramp. We have 2 balls of the same mass. We roll them down, one route down the ramp, and it impacts the ball in the center of the frame. Again, I'm going to put up a little info card up in the top right corner of the screen, and that will link you to a video of this actually happening. So this is an experiment you do, and then you can see, does the ball actually move off at 45 degrees, like the pool ball question. So the question says, how can you make this a better experiment? And there are a bunch of different answers to this. You could mark the tabletop with a complete grid of squares, and so, or do it on graph paper, and that would enable you to see exactly where each ball was moving and able to freeze frame the video and plot exactly where those balls were going. and that will give you a much better position determination. You could make the ball bearings smaller. That makes them more difficult to see on the camera, but you could do because that helps you pinpoint exactly their location if your camera has a high enough resolution to pick them up. But this also reduces the percentage errors in the trajectory. You could shoot it in a bunch of different modes. You'd have to shoot it in very high definition. The video you're seeing was filmed on my previous iPhone model, which I think was an iPhone 4S. And so the resolution is not that good, but when we do it in the future, we'll take whichever one of you has the most techie phone and film it that way. Then we will take the footage and we will reduce it in time, freeze by frame, and then we'll see what the trajectory are. All right, well, thank you very much for listening to me ramble, and I hope that was helpful to you. For my year 12s, you now have a small bunch of exam questions that I have given you the mark scheme for. I'd like you to go through those, please, and send them in the normal way. After that, you have an assessment with the lovely Miss Kennedy. So thank you very much, and what I want you to do now is stay safe, and I will see you all very, very soon.